My third video for my module over proving trig identities, and we're going to look at a few what people might call more complex examples, but these are just basically going to involve a little bit more algebra and also some Pythagorean substitutions essentially. So let's go ahead and say that you'll want to memorize these three examples because you'll find a lot of examples that are, or at least problems that are a lot like these. Okay, so starting with letter A, hey, letter A. Let's go ahead and use our guidelines that we've been using in the past for what should we do here, which side should we work with? And it looks like to us, I hope, that the left side is the more complex of the two sides. So we work with the left side. We're going to try to turn the left side into the right side here, okay? So the first thing I want to point out is this. Whenever you have like 1 minus sine squared or 1 minus cosine squared, it is simply the fact that that is a difference of two squares. And recall that a difference of two squares, algebraically speaking, can be factored into a plus b, a minus b, if the original expression was a squared minus b squared. So in this instance, we see that we have 1 minus sine squared of x. So in this case, we'd say 1 minus sine squared of x would be the same thing as 1 plus sine of x over 1 minus sine of x, okay? Or times 1 minus sine of x. So that being said, we can actually take this expression on the left and rewrite it as 1 plus the sine of our angle times 1 minus the sine of our angle. And this is all on the left side here. And this is all over, excuse me, 1 plus the sine of x on the bottom. And the nice thing about this is, algebraically speaking, we factored it down. These 1 plus sine of x, those things, they cancel. And what we're left with on the left side is this then. Well, then we just have 1 minus sine of x is the only thing we have left. That's this expression right here. But that goes to show that the left side was able to be turned into the right side. So if that's the case and we say QED, that's what I wanted to show, that's what I wanted to prove. And so the left side and the right side are equivalent expressions, okay? So on to letter B here. Speaking of differences of squares, hey, you say a squared minus b squared is the same thing as a plus b, a minus b, conjugate pairs here. It is also the case that a to the fourth minus b to the fourth, that is considered a difference of two squares. And the reason why is because we could rewrite it as a squared minus b squared squared. So that being said, that would factor down into a squared plus b squared and a squared minus b squared. See, this is all just algebra here, okay, essentially. But thing is, if I'm looking at this expression here on letter B, I'm definitely going to be working with the left side, the left-hand side, the LHS, because it's the more complex of the two. But I'm going to point this out here. We say cosine to the fourth minus sine to the fourth can be rewritten then as this. We say cosine squared of t plus sine squared of t times cosine squared of t minus sine squared of t. Okay, so far all we've done was factor the left-hand side. So now the thing that makes this expression pretty profound are two things. One, it has a monomial divisor. And two, one of my favorite properties or identities on the planet happens to be apparent right here. Get used to this, but whenever you see cosine squared plus sine squared, recall that our Pythagorean identities state that cosine squared of an angle plus sine squared of an angle, this always equals one of my favorite numerals, 1. So what this means is we could replace this out with a 1 and we get this expression here. We say cosine, oops, let me get that out of there, cosine squared of t, this is coming from this expression here, minus the sine squared of t is now all over this monomial divisor this. Okay, so now so far we've turned the left-hand side into this expression right here. Just to take a quick respite, what I want to do is recall that, hey, we're trying to get the left-hand side to look like this here, 1 minus tangent squared. So right now, looking at this, I say, well, how am I going to get, 1 minus tangent squared? I know tangent is sine over cosine. Tangent squared, maybe I can get this sine squared over cosine squared to work for me here. I have this minus right here, and last but not least, we say, well, where's the 1 going to come from? If you haven't noticed, we have a cosine squared and a cosine squared here. But the bottom line is one more quick algebra plug here is this. If you had a monomial divisor like a plus b over c, this is able to be rewritten as a over c, so the first term over the divisor, plus now the second term on top over the divisor. Oops, that's not supposed to be a b. It's supposed to be a c. A over c plus b over c. So in this instance, we're going to use this monomial divisor to rip this apart. And so we can now say this. We could say cosine squared of t all over cosine squared of t. Now minus sine squared of t all over cosine squared of t. And so looking again up at what we want to get here, which is 1 minus tangent squared, this is very helpful because our cosines here cancel out and they become just 1. We say minus. Now, if sine over cosine is tangent, then sine squared over cosine squared is tangent squared, because this would be the same thing. And I wouldn't expect anybody to write this, but sine of t over cosine of t, that squared would be the equivalent expression here. But we get this, we get 1 minus tangent squared. It's just worth your time knowing that sine squared over cosine squared is tangent squared, and like sine to the fifth over cosine to the fifth would be tangent to the fifth. You know, any sine to the n, you know, over cosine to the n would be tangent to the n. But we were able to turn the left-hand side into the right-hand side, which is what we wanted to show. This is what we want to show: 1 minus tangent squared of t is equal to 1 minus tangent squared of t. So check. QED, that's what we wanted to prove. Okay, so the last example here, the last one, you know, it involves a couple of sleight of hand tricks here, but I want you to look at this with me. We say 1 plus cosine of theta. I want to show that this is the same thing as sine squared of theta over 1 minus cosine squared. The thing is, the right-hand side of this is much more complicated than the left-hand side. However, get used to some Pythagorean substitutions. So what we know is this. Coming into this, we know sine squared of an angle plus cosine squared of an angle. And I know I didn't write the angle as 1. But likewise, we could say this is the same thing as sine squared. If we were to dump the cosine squared over here is equal to 1 minus cosine squared. Or if we had dumped the sine squared over here, we would have had then cosine squared would be 1 minus sine squared. It's just something to get used to. The bottom line, though, is on the top over here where it's sine squared, we could rewrite that as this: 1 minus cosine squared of, in this case, theta. So now I'd love to just divide this straight out, but I can't. But what I do know is this right side on the top over here, it's a difference of 2 squares. And so thus can be factored into 1 plus cosine, 1 minus cosine. And the reason why this is beneficial is because look at your denominator. We have a 1 minus cosine down here. And so our 1 minus cosines, those things cancel out. And what I'm left with then is just this expression here. So I get 1 plus cosine squared of theta on the right. And that is what I wanted to show that it equaled on the left in the first place. So check mark, QED. But we picked a side. We picked the more complicated side and turned it into the other not as complicated side using trig substitutions, a lot of Pythagorean substitutions on this one, and algebraic you know, manipulations such as factoring differences of squares. So cheers.